Ahora va a tener lugar Abiodun Abiola, en el que la ponencia va a tener lugar sobre the use of artificial intelligence to improve predictive maintenance in hydrogen systems. Abiodun Abiola, que lo tenemos por aquí, es ingeniero mecánico con el máster en Energías Renovables, investigador de la Universidad de Huelva, aquí, y es colaborador de la Cátedra Gabitel. Así que sin más, os dejo con Abiodun, que nos cuente un poquito. Muchas gracias.
Buenos días, yo soy Juan Andrés Reales, director de Gabitel Ingenieros, que forma parte de la cátedra Gabitel que creó en el año 2020-2021 la cátedra Gabitel del hidrógeno con la Universidad de Huelva, en la que pretendemos poner a disposición hacer de nexo de unión entre el sector empresarial y el sector universitario, que a veces no somos capaces de coger todo lo magnífico que hace, en este caso, la Universidad de Huelva en materia de hidrógeno. Había alguna pequeña transparencia de qué hacemos en Gabitel y quiénes somos, pero yo simplemente quería aprovechar para introducir a Abiodun. Es colaborador de la Cátedra Gabitel del Hidrógeno, investigador de la Universidad de Huelva, y está desarrollando un proyecto muy interesante de aplicar la inteligencia artificial a los procesos de mantenimiento y a todos los procesos en el sector del hidrógeno. No les voy a contar de la importancia de la inteligencia artificial en los últimos años, entonces nos pareció que era un tema interesante para que diera la ponencia hoy. Entonces yo, sin más, que agradecerles que hayan venido y que estén con nosotros. Voy a pasar la palabra para que él la va a hacer en inglés. Ya le hemos dicho que vaya a un ritmo adecuado para que todo el mundo la pueda entender perfectamente, pero creo que es un tema lo suficientemente interesante para que lo aprovechemos. Muchas gracias.
Muchas gracias. Gracias. Por favor, haré este discurso en English. Please allow me to speak in English. I'm still learning a bit of Spanish, so. Okay. The title of this paper is Use of Artificial Intelligence to Improve Predictive Maintenance in Hydrogen Systems. Okay. And I'll be talking about just a minute. Typical hydrogen system, and why we need maintenance, and what is artificial intelligence, and how we can use it to improve predictive maintenance. Okay. All right. So in a typical hydrogen system, we have renewable solar, wind turbine, and then we have electricity. We can use the electricity directly, to the grid, and for powering electric cars or for residential buildings. Alternatively, during long-term storage, we could use the hydrogen for powering the fuel cell to also produce electricity. For the entire hydrogen system to work effectively, we need maintenance. We need continuous monitoring of the system, and that's why we have data flowing from the fuel cell, the storage, and the electrolyzer. And there's a central unit where we take information from all of these, and we're able to monitor what is happening in our hydrogen system. The cost of investment of this entire system can sometimes run into thousands of euros, and it's good to be able to have information about our system, and we'll be able to know when to take activities to ensure it lasts longer. And then the concept of maintenance. We use maintenance for virtually all spheres of life. Even our body, we need to maintain our body. We need to go to the hospital for medical checkup. Same for the equipment. Airplanes, we need regular maintenance to ensure that we don't have crash. electrolyzer, which is what I will use for the case study. We need maintenance, combustion engines, virtually all spheres of the technical industry, we need maintenance. And then I will talk about artificial intelligence. It's a hot topic now all over the world. Everybody's talking about artificial intelligence in China. In US, there is a war on who is going to win the race in artificial intelligence. And basically what is artificial intelligence? It's making the computer or the machine to do what human being can do. And the machine is learning so fast, like a human being, such that it's able to watch the pattern of previous events and make actions and decisions, just like we have driverless cars now. Today now, we have some cars that can drive without human intervention. And we'd like to deploy this technology also in our hydrogen systems. How can we do preventive maintenance, predictive maintenance in a better way using artificial intelligence? Now, the traditional maintenance is classified into reactive or preventive maintenance. That is, when it's reactive, we wait for a fault to occur, and then we go and take an action. But that doesn't help our investment. Just like our human body, if we wait for us to get sick before we go to the doctor, the lifespan, gets reduced. But in this case, we like to take action before the fault, and that is more of proactive maintenance. But the focus of this paper is on predictive maintenance, which is forecasting problems in advance and then taking action to prevent it. And in predictive maintenance, we basically use sensors to capture information from our hydrogen system. And the sensors, they do various activities, such as controls, fault detection, And for this paper, we'll be talking about the temperature sensor and its criticality to electrolyzer plants. Temperature is an important process parameter that give us information about how healthy an electrolyzer is. If an electrolyzer is in operation, high temperature also gives us an information on how efficiently it's able to convert electricity that it receives into hydrogen. If an electrolyzer is receiving 10 kilowatts of power, and then the hydrogen that it is producing, it's say 5 kilowatts. The rest is dissipated as heat. So that temperature gives us information about how healthy our electrolyzer is. But there could be a problem if you have predictive maintenance that is using this sensor to check the health of our electrolyzer. What if the sensor fails? It means the predictive model is going to fail. The predictive model will not be able to predict when the electrolyzer has fault or will have fault. So in this case, we want to use artificial intelligent concept, AI, to be able to predict the temperature sensor data. And this is a case study that we'll be looking at. We have an electrolyzer and various sensors attached. In particular, we're interested in this temperature sensor as a case study. And we have a programmable logic controller, which is one of the common controllers that industrial processes they use to control electrolyzers. And in most industries, we have a SCADA system where you transmit information through TCP or wireless communication. And we could host our artificial intelligence model on some of these SCADA systems at no cost. At no cost, just to have a AI model that is deployed on the same SCADA network that is able to track information about some of the sensors we are interested in, and also be able to predict the sensor information such that when it fails, we are still able to utilize our predictive model. The methodology we proposed in this study is divided into 4 phases. The phase 1, basically we do pre-processing of electrolyzer data. This is one of our experimental data from the electrolyzer. And we have some process data that has been captured. We have the pressure, which is the blue line from the electrolyzer. We have the voltage, the stack voltage. Then we have the cooling water temperature, the gray line. Then we have the hydrogen temperature, which is the orange line. In this case, we are using the hydrogen temperature sensor, the TT121, as the sensor of interest. If it fails, how can we make prediction? Now, we need to process this data before we feed it into our AI model. AI model will not predict accurately if you just take all this data and feed it into it. The reason is that some parameters are within a higher range, some are within a lower range. For example, if we feed all this data into the AI model for us to predict TT121, we'll have a lot of error because cooling water temperature is within 23, 24 thereabout, is kind of higher, while we have the voltage within 11, 12. So we need to do what we call normalization or standardization. And basically, we use the form of Z-scoring. There are several types, which is for us to have a mean of 0 and a standard deviation of 1. This data now, when we process it, they all become of the same range, which we will now have as our normalized data. We can now use this processed data and feed into our AI model for predicting our TT121, which is the hydrogen temperature sensor. So that's phase 1. And then we come to phase 2, which is a question of, we want to predict hydrogen temperature sensor, which is TT121. But the question is, which of these other sensors can we use as our backup to take information and make prediction? Is it the voltage? Is it the cooling water temperature? Or do we combine 2 or 3 data together? We don't know. And that brings us to the problem of feature selection. To solve this problem, we use what we call the deep reinforcement learning algorithm. DRL is also a subset of machine learning, and then is basically we have a software robot that has an agent, and the agent seeks within this space of features to search the relationship between all of these variables with the TT121 to see the one that has the highest correlation to the hydrogen temperature sensor. So the agent takes action by taking one after the other these features and compare with the TT121. And the one that gives the lowest root mean square error is the one that the agent selects as the best one to make the prediction. So it's basically like a software agent inside the AI model that does that feature selection for us. And this is a model that's developed in the MATLAB for doing that. And basically, we have the DRL agent, and then it takes information. Then it also has what we call a reward system. If it picks a feature that gives a very high error, the reward will be very low. If it picks a feature that gives a very low error, then the reward is high. So the target of the agent, what the agent is seeking, is to have the highest reward as it is doing simulations around the computation. So at the end of the simulation, whatever gives the lowest error is the feature that we take for input into our AI model. And this is just a plot of the actions of the AI model. We have the number of the agents and the features. Like 5 is the feature 5, feature 1 and feature 2. Feature 2 is basically the TT105, which is the cooling water temperature, and these are the errors. And the result of the simulation shows that it has made a selection and is no longer taking any other search in the system. And we compare the selected variable, which is the TT121, which is hydrogen temperature, with the cooling water, and we see that there is a high correlation with the same results from the model. Now the next phase, which is the last phase, is to use another model which we hybridized with the DRL called the long short-term memory network to now make prediction. And the essence of it is to train it. When we train it, we feed the selected feature into the LSTM, and then we are able to use it to make a prediction. And this is the model in MATLAB, where we can use the graphical user interface, or we can do the modeling in the MATLAB program. And we do also some optimization to reduce the error further. We work on the gradient threshold. We have the number of layers. We have what we call the dropout factor. There are various parameters that we use to reduce the error. And these are the training. When we see that the error is the minimum that we can get, we can use the model for prediction. And finally, this is the result of our prediction. The actual temperature sensor is in purple line, you can see. And when we feed the cooling water temperature into the model, we can see that it's able to make the prediction that is very close to the actual sensor. And the RMSE, which is the root mean square error, is 0.1351, which shows that our model is able to make prediction with very low error. And that's what we have done so far with the use of AI in hydrogen technology. Thank you for listening. Gracias.